Gelfand duality. Yes, please.
Yes. So I want to talk about Gelfand duality, and before moving to the actual content of this, I want to give some meta motivation for why we want something this kind. So traditionally, mathematics is divided into several subfields. Probably the two main important ones are geometry and algebra. And this division does not quite make sense because mathematics is all interconnected. There are connections all over the place, but morally, intuitively, there is distinction. There are different kinds of thinking about mathematics. And maybe, although it's impossible to give a formal definition of what geometry and what algebra is, I can give some examples of what the two things study. So what does geometry study? For instance, it studies manifolds, so all the things that appear in models of physics when you want to have some model of, I don't know, some kind of string theory or something like this, you pass to some kind of manifolds or complex manifolds. If you look at the Euclidean space, it's also an example of a manifold. If you look at the projective space, you might have also seen it. It's also a manifold. Some kind of moduli spaces. So when you want to study some more combinatorial problem, you can classify all the solutions and they turn out to form some kind of space again. So the space of curves of genus G with n-marked points, the space of graphs, the space of hinges, like if you want to study robotics, there are hinge mechanisms. Also metric spaces is another example. So if you have some data set, you want to analyze it, and one way to do it is you compute the distances between all points, and all of this data together forms a metric space. But you can study that using some other methods, some geometric methods. On the other hand, algebra doesn't study these kind of objects that have physical intuition behind them. Well, it might, but the way we think about what algebra does is in terms of structures. So algebra studies structures that appear throughout mathematics in different areas, and most likely these are the structures that appear more often that are more interesting, but sometimes it's also structures that algebraists think are important, maybe not have as many examples. But some examples that you've probably seen are groups. So if you study basically any type of mathematics, there are some group theory involved. There are symmetric groups, there are dihedral groups, there are cyclic groups, all these kind of things that allow you to study symmetry of objects. There are rings. So rings are something that looks like numbers. It's something where you have addition, you have multiplication, you have unit and zero, and you have all these operations, you have all these compatibilities, all these properties of these operations that numbers have. So the multiplication and the addition have to be associative. The addition has to be commutative as well. There are additive inverse, and the multiplication distributes with the addition. I'm not writing down the formula, but I mean, if you've never heard this word, it doesn't matter that much. The important thing is that we have some operations on a set. There are also categories that probably within this subfield. I'm putting it in a separate bullet point because they do not count as a set with a structure, but more like a graph with a structure, something like that. In any case, so the difference is somehow that intuitively the way the intuition. In mathematics, definitions are important. So whatever you do, you can say things, but there has to be a formal definition behind. You might not think in terms of this formal definition. You might have a separate intuition about the objects. And geometry is where this happens a lot. So if you were to actually define a smooth manifold or something like this, the definition is horrible. But if you want to explain what it is to middle schooler, you would be able to. It's not such a big deal. The intuition exists, and it is somehow exists in parallel to the formal definition. In algebra, on the other hand, the intuition is basically the same as the formal definition. That's the idea, that you study the structures the way they are. That's how you think about them. So in particular, there is a difference in how we interact with this. So if we want to prove some theorems, of course, we would use also some arguments that mimic intuitive arguments, but we have to be very well versed in the language and understand very well what happens behind what we do. Well, here we can often, for instance, formally verify. So one of the first theorems, big theorems that was verified on a computer was, what is it called? I forgot the name, but there was a theorem about was a complicated result in group theory whose proof was taking maybe 100 of pages. And this was easily verifiable using the first proof assistance that ever existed. And this is nothing that one can dream of on this side, because the formal language is just way too involved. And so what Gelfand duality is about is that, in fact, there is a correspondence between these two worlds in a very precise sense. So one thing that one usually uses as a formal formal mathematical definition behind all of these objects is a topological space. So there is a topological space, and basically any geometric object that you can think of, this is not exactly true, there are some other examples, but basically all of the geometric objects that you can think of have an underlying topological space. So if you have an algebraic variety over complex numbers, the has an underlying topological space. If you have any of those mentioned, you also have an underlying topological space. And everything else can be thought of as some additional structure in topological space. So somehow this is a fundamental notion. This is thought of as a fundamental notion. And so what can we do if we have a topological space? What can we talk about? It has points, so we can say sentences like, I have a point on a space. I have 2 points on a space, they're equal or not equal, something like this I can say. I can also talk about open subsets. So this is slightly maybe unfamiliar notions to those who didn't study topology, but basically what it means is that you have, in terms of convergence, it is a subspace that doesn't contain any boundary points. Subsets. And the other thing that you have for topological space is a notion of continuity. So you can look at functions, just functions in the set theory sense, and you can say that the function is continuous. I want to claim that this is the most important notion of all of this. You don't need to think about points, you don't need to think about open subsets. You just need to think about continuous functions. So for given space, I can look at the set of all continuous functions. I denote it like this: C, well, my space is X, C, X, C. This is an indentation. This is a set. It has multiplication and addition, because I can just take functions and multiply and add them on values, value-wise. It also has a structure of a Banach space. So this is a more complicated notion that I don't want to delve into, but it's some kind of structure that often appears in functional analysis in PDE. So it has, first of all, it has a structure of a C vector space, but also it has a norm. So it has some compatible. It has some compatible norm with the vector space structure, and altogether, so there's a little bit more, but altogether it actually forms what's called the C-star algebra. And this, I mean, although it has a norm, so this might be a bit questionable, but everything we know, everything that we do with C-star algebras is more on this side than on that side. It's more algebraic. It's an actual algebra. You can talk about all this. You can manipulate symbols in there, and you don't actually think of it geometrically. You think about it algebraically. It's much easier to verify statements. It's much more naive in that way. And so the theorem of Gelfand which is mentioned in the title, is that this, so given a space, I form this set and I view it as a sister algebra. This defines a correspondence between compact Hausdorf topological spaces and commutative sister algebras. So given a space, I take this sister algebra, and Gelfand theorem tells you that this correspondence is 1-to-1. Now I have to be very precise in what I mean by that. So usually when you say 1-to-1 in mathematics, this means that there is a bijection. So there's a function in the other direction, and the two composites are equal to the identity, right? So there's an inverse map to this one. And there is an inverse map, so there is something I call character space, so char, of an algebra, of a commutative sister algebra. This is a topological space. And for any space is isomorphic to the application of the character, of taking character space of its space of continuous functions. And the other way around, any sister algebra can be recovered as continuous functions on its space of characters. So where's the catch? The catch is here I'm using the word isomorph, not just inequality. And this is important to keep in mind. But from the practical perspective, from the way we do mathematics, it has to be thought as 1-to-1. Because so in fact, we don't just have a correspondence of just like sets of these objects and these objects. We have, in fact, an equivalence of categories. So I don't have much time to talk about what a category is, but the modern perspective is that any type of mathematical object you can view using category theory, and instead of studying the specific class of objects in the direct sense, you can just study the category of these objects. And if you change the category to an equivalent category, all the statements will transfer. All the reasonable mathematical statements will transfer. And so in this sense, here, if you want to study compact Hausdorff topological spaces, we can equivalently study commutative sister algebras with the relations inversed. So category has objects, it has relations between the objects, and the relations are directed. You can invert the relations. So they have the same information, but it's reversed. This in fact forms this in fact forms a category, this in fact forms a category, and this is an equivalence between them. So the duality is because we need to, it's called the duality because we need to invert relations. And how many minutes do I have?
Oh, almost.
Yeah. So then I'll just make some final remarks. So, of course, this is an interesting statement on its own. So people use it. It's a very old theorem, in fact, and people have been using it for many decades. But what my role in how I approach a similar statement is that there is, in fact, this kind of equivalence in other geometric contexts. It doesn't only exist for topological spaces and sister algebras. In fact, the one equivalence that is more familiar to me is where I have some kind of algebraic varieties here and arbitrary algebras here without any C-star, I think, involved. And there are also versions for topological spaces, so some kind of generalization of smooth manifolds. And all of this suggests that this is not just a fluke. This is, in fact, something fundamental about how we view geometry and algebra, that there is some kind of way to go from one world to another and backwards. And this is helpful in practice, this is helpful for both sides. And the other remark I want to make is that in geometry, often one wants to consider some kind of generalized spaces, and there's not that much room for improvement. Like there are some topological spaces for some kind of algebraic varieties, but sometimes you want some properties that just cannot be expressed geometrically, and there's no room for generalization if you just view spaces as spaces. But on the other hand, if you view them as algebras, you can try to relax some assumptions. Instead of looking at commutative algebras, you can look at non-commutative algebras. And this gives rise to non-commutative geometry. Or you can get rid of the notion of invertibility of existence of inverses for addition. You get some theory of semi-rings, and on this side there will be some kind of tropical geometry. So there are ways to approach geometry using algebra only, and this gives you some completely different new worlds that are impossible to define directly. And that's about it.
So, any question from the non-expert, young researchers? Yes,
thanks for the talk. I don't think you mentioned it, but is there any, was this duality used practically to prove a theorem on one side using the representation that you get from the other side?
Yeah. There are a lot of results that go this way. Yeah. I mean, I don't think I have a good example in mind right now, but yeah, it's a very classical result that is used both in the theory of sister algebras and
the abstract implication. It's not so abstract as a result that you cannot actually use it. It's actually.
I mean, I don't know if you can answer with this directly, but yeah, it is applied in results in physics.
So, any brief?
Yeah, so I do phylogenetics, and the biggest problem in phylogenetics is searching for the best topology in a big topological space. And then we typically do heuristics because we believe it's impossible to understand the shape of the topology space. Was there any attempt to use algebra to understand the shape of topology space?
What do you mean by shape?
For example, like there is a valley and there is some hills based on some functions, or was there any connection?
I mean, you can just in this sense you can just recover the space using functions. I didn't say specifically what characters means, but there's a notion of an ideal in an algebra, and you can some kind of ideals define your points in the topological space, and you can recover it. But I'm not sure if algorithmically this is more of a kind of fundamental result. I'm not sure if you can like use it computationally to analyze, Yeah, it really depends on what you mean by things like, hill or valley. Maybe let me give you a different answer. So one way I know how to interpret the notion of a shape is using commutative theory. So if you have a space, it might have some holes, it has some, in your case, maybe you need to cut the space in levels, and then you can see whether there are holes or not. Depending on this, there will be a hill or not. And so this commutative theory is there is a way of taking a space, and this is computational. There is a way of looking at some space defined by some combinatorial datum, and there is a way to get some algebraic invariance of this, which will be computable, which would be numerical, very nice. And one thing that you can do is some kind of invariants are not just defined for spaces, but they also define for arbitrary algebras. And they are sometimes, in many cases, when this happens, they're also more computable. So some invariants like this, I can just throw words. So K-theory, this is something that I do, is defined for arbitrary sister algebras, and occasionally it is computable. But I'm not sure if for these practical questions where you already have the data given by points, it will be easier to pass to algebras and compute this rather than just doing it directly.
Yes, please.
Well, you may have mentioned this in passing, but so this theorem is for this compact topological spaces corresponding to this algebra. But so is there any like example that one can you can define, let's say, algebra, but then you cannot find any geometry that corresponds to that. So my question is like space of algebra and space of geometry, which one is larger? Or
These are algebra is larger.
okay, so you can find examples that you can define algebras, but
So I mean, this is one-to-one as written, but the generalizing these to like non-compact Hausdorf spaces is not as big as generalizing these to non-commutative algebras. And so if you pass to the non-commutative world, you'll get it's so much larger. There's so many new phenomena, so many more new phenomena here. So I think this is strictly bigger.
I think I'm not young, but
You're also an expert.
no. Well, yeah, my question is related to his. Where, yeah, so where in biology or in statistics, where people often talk about the landscape of distribution or also the distribution of probabilities. So, for example, where Amari-san introduced a notion of information geometry. So I'm wondering where if there is a corresponding algebraic structure to that information structure.
So I don't think I know. You said information
geometry is
information.
yeah. So what he introduced is that various probability distributions can be considered as a kind of space. The simplest case is that so restricted to, for example, Gaussian distribution, it has a mean and variance. So two parameter space. And what he shows that that parameter space is described by some kind of curved geometry. And of course, more generally, if non-Gaussianity is introduced, more complicated space to describe the probability distribution, a set of probability distribution. Yeah, so I think that question is related to the previous one. So in describing the diversity of biology, or in such a case, people often use the concept of landscape. Yeah, so it's a kind of manifold geometry.
Yeah.
So yeah, I'm wondering if there is any corresponding algebraic structure.
I would have to look at the definition.
Yeah.
Maybe.
As far as I understand, in the definition they use Riemannian manifolds. So maybe we can reduce the question to Riemannian manifolds. There are some great pointers to Riemannian manifolds.
Yeah, the simplest case I think is Riemannian, but not necessarily. Yeah.
No, not necessary. I think sure. So that's actually good.
I don't know.
But I mean, very simply, okay, this isn't necessarily Fisher information metric, but if you take the Wasserstein metric on your space of probability measures, certainly if your original space is compact, then your space of probability measures is also a compact metric space. So it's a compact topological space. So it will have a C-star.
Yeah, so maybe it's worth mentioning that defining like an error in this direction is basically always possible. You can always take functions such as this. It's harder to go back.
If you have additional structure and metric, then you will try to know what first should that
Yes.
structure.
It's not clear whether the additional structure you get here will be sort of algebraic. Will be it's familiar to algebraics.
I mean, complex defined central trick.
Yes.
So any other question?
Yeah, I guess non-commutative space is closely related to non-commutative geometry. And so how much is some physicists said that it's kind of non-commutative space. So how much is known about the extension of the non-commutative fields?
Yeah, so basically there's no acceptable definition of what a non-commutative space is if you define it sort of geometrically with underlying topological space. But there are things on this side, and it's the statement more like allows you to define what you mean by non-commutative geometry by saying that, okay, just dual to whatever it is on this side. And this is how people approach it nowadays. So say in derived non-commutative geometry, it turns out that everything, all kinds of spaces are even better if you instead of the algebra functions, you consider sort of the category of some kind of shifts on the space. I don't want to say what a shift is, but some kind of shifts on the space. It turns out to be a category, not an algebra, but an algebra is recovered from this category. And then if you view this as your notion of a non-commutative object, then it's more robust. You can say many things which you would like to say.
Okay. Can I ask another question? So despite the non-commutative space itself has a does not have a good definition, but sometimes physicists expect that there is a quantum field theory on non-commutative space.
So I think the idea is you sort of have to extend your understanding of what a space is to something that does not intuitively feel like a space. You use it using the right hand side.
Just a scalar field is a function, and just you place it the function as whatever that you need here, whatever non-commutative function. So just repeat. So for just a scalar theory, we are passing integrating over the space of algebra space of functions, and just replace it the whatever non-commutative algebra with good notion of measure.
Yeah.
That's kind of more strict. I think it's more strict than really thinking about the geometry. Because we are implicitly already thinking about functions.
Yeah.
Maybe one thing to say here is also like there are natural ways to talk about. So if you have a space, you can talk about its open or closed subsets, and often you can specifically about open and closed subsets. You can also think in terms of algebras. You can take the algebra functions, and then a closed subset in a space corresponds to the quotient algebra, so it's surjective homomorphism of algebras. And other things that you want to do, so in the end, when you want to say something about geometry, this is what you need. You need the notions of closed things, you need the notions of, I don't know, maybe intersection theory or something like this, and you can do it in this setting. You can do it in this world, completely ignoring the fact that you don't understand how to do it geometrically. Not to do it with the physical intuition.
Okay. So any other question, including from the expert? So I have a question. So could you give me some simple example of its corresponded by using the group algebra of Abelian group or something?
Group algebra from like what corresponds?
Yeah.
What will correspond? Yeah. So for group algebra, if you take the character space, this will be the space of it will be the space of characters of G.
Okay.
I guess I should also use this notation. I was thinking,
Yes. Suppose, for example, that G is a U1 group, or then character is.
So, for instance, if you start from S1, this will give you the integers, and this is the basis for the Fourier transform.
So is it a kind of Fourier transformation? So generalization of Fourier transformation. So the space is specified by each point, but on the other hand, where Fourier transformation or where some complete where function of in a complete basis is where it's an extended.
I think you can deduce the Fourier transform for like compactly groups using this compactly groups. But it's I think the statement's slightly different in flavor. They form equivalences between different categories. But I think you can use Fourier transform.
And you mentioned about the tropical geometry.
Yeah.
And so the corresponding algebra is, you said, not reversible. Where,
yeah, I think this is something called semi-rings. I don't know much about this myself, but yeah, there is some kind of algebraic code to functions.
Dualities are already established. And,
I think you need to look at some kind of affine tropical, right? Well, there is an expert somewhere.
Yes, it's
so maybe the expert has not been.
I think there you include what we should consider for the algebra side.
It's not clear what to consider the algebra side.
Yeah, for instance, we can consider just a piecewise linear or piecewise affine function on the algebra side, but we consider such functions, then probably that corresponds has not been established.
Yeah, I think in tropical geometry, the different thing is that for Eurogeometry, the space of function and for example, for affine space, the space of function and the space of polynomial ring is the same thing. But in tropical geometry, the space of function is not the same as space of polynomials. Right.
Yeah, but then there has to be the precise notion of a function.
Yeah. What I mean is that what I understand is that for now there is a well-developed theory for polynomial rings over semi-field, but the corresponding abstract notion of tropical curve has not been developed. Meaning that the functions are not well studied, but polynomials are yes somehow
I see.
well understood. Yes. So in this sense, we still do not know much about the functions. Yeah, but the coordinate ring is yes.
Yeah, so apparently it's not.
Any other question? If not, thanks, Vladimir.